Hello. Our group consists of three members: Eric Brown, Humberto Frenier, and Javier Izquierdo. And the paper our group chose to present is a comprehensive evaluation of cryptographic algorithms. In today's internet era, with online transactions almost every second and terabytes of data being generated every day on the internet, securing information is a challenge. Cryptography is an integral part of modern world information security, making the virtual world a separate place. Cryptography is a process of making information unintelligible to an authorized person, hence, providing confidentiality to genuine users. There are various cryptographic algorithms that can be used. Ideally, a user needs a cryptographic algorithm which is of low cost and high performance. However, in reality, such algorithm, which is a one-stop solution, does not exist. There are several algorithms with a cost-performance trade-off. Thus, amongst the cryptographic algorithms existing, we choose an algorithm which best fits the user requirements. In this process of choosing cryptographic algorithms, a study of strengths and weaknesses of each algorithm will provide valuable insights. In our presentation, we will discuss popular cryptographic algorithms such as DES, 3DES, AES, RSA, and Blowfish. The Data Encryption Standard, or DES, is a block cipher, meaning a cryptographic key and algorithm are applied to a block of data simultaneously rather than one bit at a time. DES was founded in 1972 by IBM using the data encryption algorithm. It was adopted by the government of the USA as standard encryption algorithm. It began with a 64-bit key, and then the NSA put a restriction to use a DES with a 56-bit key length. Hence, DES discards 8 bits of the 64-bit key and then uses the compressed 56-bit key derived from the 64-bit to encrypt data in a block size of 64 bits. To encrypt a plaintext message, DES groups it in 64-bit blocks. Each block is enciphered using the secret key into a 64-bit ciphertext by means of permutation and substitution. The process involves 16 rounds and can run in 4 different modes: encrypting blocks individually or making cipher block dependent on all previous blocks. Decryption is simply the inverse of encryption, following the same steps but reversing the order in which the keys are applied. For any cipher, the most basic method of attack is brute force, which involves trying each key until you find the right one. The length of the key determines the number of possible keys, and hence the feasibility of this type of attack. DES uses a 64-bit key, but 8 of those bits are used for parity checks, effectively limiting the key to 56 bits. It would take a maximum of 2 to the 56 power attempts to find the correct key. Even though few messages encrypted using DES encryption are likely to be subjected to this kind of code-breaking effort, many security experts felt that the 56-bit key length was inadequate even before DES was adopted as a standard. Even so, DES remained as a trusted and widely used encryption algorithm through the mid-1990s. However, in 1998, a computer built by Electronic Frontier Foundation decrypted a DES encoded message in 56 hours. By harnessing the power of thousands of network computers the following year, EFF cut the decryption time to 22 hours. Apart from providing backwards compatibility in some instances, reliance today upon DES for data confidentiality is a serious security design ever in any computer system and should be avoided. There are much more secure algorithms available, such as AES. DES will keep the content safe from honest people, but it won't stop a determined thief. Despite having reached the end of its useful life, the arrival of the data encryption standard served to promote the study of cryptography and the development of new encryption algorithms. Until DES, the cryptography was a dark art confined to the realms of military and government organizations. Triple three Triple DES, or 3DES, is another mode of DES operation. It takes three 64-bit keys for an overall key length of 192 bits. In Stealth, you simply type in the entire 192-bit key rather than entering each of the three keys individually. The triple DES then breaks the user-provided key into three subkeys, padding the keys if necessary so they are 64 bits long. The procedure for encryption is exactly the same as regular DES, but is repeated three times, given the name triple DES. The data encrypted with the first key, decrypted with the second key, and finally encrypted again with the third key. Triple DES runs three times slower than DES, but is much more secure if used properly. The procedure of decrypting something is the same as the procedure for encryption, except it is executed in reverse. Like DES, data is encrypted and decrypted in 64-bit chunks. Although the input key for DES is 64 bits long, the actual key used by DES is only 56 bits in length. The least significant or the rightmost bit in each byte is a parity bit and should be set so that there is always an odd number of ones in every byte. These parity bits are ignored, so only the seven most significant bits of each byte are used, resulting in a key length of 56 bits. This means that the effective key strength for 3DES is actually 168 bits, because each of the three keys contains 8 parity bits that are not used during the encryption process. 3DES is based on the data encryption standard algorithm. Therefore, it is very easy to modify existing software to use triple DES. It also has the advantage of proven reliability and a longer key length that eliminates many of the attacks that can be used to reduce the amount of time it takes to break DES. However, even this more powerful version of DES may not be strong enough to protect data for very much longer, due in particular to the small block size. As such, the DES algorithm itself has become obsolete and is no longer used. The National Institute of Standards and Technology, or NIST, ratified AES, the Advanced Encryption Standard, as a replacement for DES. NIST endorsed triple DES as an interim standard to be used until AES was finished. Although AES is at least as strong as triple DES, it is significantly faster. Many security systems may support both triple DES and AES, where AES is the default algorithm. Although 3DES may be maintained for backward compatibility, it is no longer recommended.
AES, or Advanced Encryption Standard algorithm, was developed in 1998 by Joan Dement and Vincent Richmond, and it is a symmetric key block cipher. AES algorithm supports any combination of data and key length of 128, 192, and 256 bits. And also it allows a 128-bit data length being split into four basic operational blocks. These blocks are considered arrays of bytes and are organized as a matrix of the order of 4 by 4, which is also called as a state and subject to realms where various transformations occur. AES is stronger and faster than triple DES. Can be implemented using Java or C. For full encryption, the number of rounds used is variable. It could be 10, 12, or 14 for the key length of 128, 192, and 256 respectively. Each round of AES uses permutation and substitution network, and it is suitable for both hardware and software implementation, as long as the keys are different on each use. RS8 was founded in 1977, and it is a public key crystal system. RS8 is a symmetric cryptographic algorithm named after its founders, Rivest, Shamir, and Adelman. The way it works is by generating two keys, public key for encryption and private key to decrypt the message. RS8 algorithm consists of three steps. First one is the key generation, which is used as key to encrypt and decrypt data. Step 2 is encryption, where the actual process of conversion of plain text to ciphertext is being carried out. And last but not least, we have a third step, which is called decryption. This is where the encrypted text is converted to plain text at the other side. RSA is based on factoring problem of finding the product of two large prime numbers, as we'll see in our next slide. The key size could be of 1024 to 196 bits. The first step of the process is creating two large prime numbers, P and Q. These numbers are very large, at least as we mentioned in our previous slides, 512 bits digits or 2024 digits, which is considered safe based on the current development of computer systems. After that, a modulus needs to be computed, and these modulus will be generated out of the large two prime numbers that we picked up in our first step. After that, a totem needs to be created, and the way the totem is calculated is using p minus 1 and q minus 1, which are the first two numbers that we came up with in the first step. After that, we're ready to create our public key, and our public key is created based on our one of the prime numbers calculated from the range of 3 totem of n that has a greater common divisor of 1 with totem n. Once the public key has been generated, we can proceed to generate the private key. Because of the prime in step 4 has a GCD of 1 with totem n, we're able to determine its inverse with respect to mod totem of n.
Thank you, Humberto and Javier. The next standard we would like to present to you is the Blowfish Symmetric Standard. Blowfish was first created in 1993 by Bruce Schneier as an alternative to DES and the IDEA standard. Other notable attributes of Blowfish are that it uses a 64-bit cipher block, which means that a block size of 64 bits of data is encrypted at a time. Also, it has a variable key length, which could vary from 32 bits on up to 448 bits in size, thus increasing the difficulty of Eve to try and guess the shared key being used. It has a very fast encryption time and is used in a great number of cipher suites and encryption products to date. The algorithm is based off the Feistel structure, which basically splits the plain text up into left and right sides, with the left side exclusively ORed and its output fed into a F function and used as an input combined with the input of the right side exclusively ORed together to then have the left and right sides swap outputs and perform 15 more rounds of the same array to create the ciphertext. In a later slide, we will show an illustration of this process. In this slide, you can see the figure illustrating the flow of the Blowfish algorithm. The plain text is split in half with the left side exclusively ORed and fed into the F function, whose output is exclusively ORed with the right side part of the plain text. The outputs are swapped and repeated 15 more times to create the ciphertext to be used. As mentioned in an earlier slide, Blowfish is a pretty fast encryption software as compared to some of the others we have compared in this presentation. This illustration shows a comparison of encryption and decryption speeds of variable file sizes of the different encryption standards presented. Blowfish is noticeably faster than the others, with average encryption and encryption times of 72.4 megabits per second and 88.7 megabits per second, respectively. Therefore, if speed and a light processing imprint is what you're looking for in encryption software, then Blowfish is a highly recommended choice. We have now come to the conclusion of our presentation on cryptographic algorithms. We have provided you with a high-level overview of the different encryption standards such as DES, triple DES, AES, RSA, and Blowfish. We have touched on their strengths and compared their speeds. We hope that you have obtained a clear understanding of how the different encryption standards work and also have gained a sound baseline on which standard to choose based off your need to use an encryption standard. Again, I would like to say thank you to my co presenters, Javier and Umberto, and thank you for listening to our presentation.